We can leave that. Oh, sorry. And then we can leave that conversation to talk about other things in life that have been created by engineers. After that, now that they are starting to think about engineering and they're starting to notice all the things around us that have been created, we talk about different types of careers that have engineering in them. So on the board, you're going to see a bunch of different examples of engineers or jobs that require engineering. Now, this is not all the jobs because there are so many that require engineering. However, the ones on the screen are just the ones that are most common to our students. Are there any questions so far?
Hello.
Hey.
Just checking.
Yes. Can you hear us?
Yes, we can hear you.
Okay. No questions so far?
No questions.
Perfect. So then I give them the actual definition of engineering. Engineering, and it's on the screen in front of you. I'm going to read that to you. It says, engineering is the process of creating and building structures, products, and systems by using math and science. There are two things in this definition that I like to talk to students about. One is the aspect that engineers create systems. We categorize systems as any small parts that work together to create something bigger. So an example of that would be a bicycle. You know, a bicycle is wheels, pedals, handlebars, but all of these pieces work together to create a bigger bicycle. And systems also can be incorporated with websites, applications on the phone, and that's computer science engineering, which is another type of engineering. The other aspect I like to point out is math and science. So we're creating something using math or science. However, this is something that students typically do their entire lives. I give an example of a block tower, like a 4-year-old or a 5-year-old building a tower of blocks. When you do that, you are using geometric thinking and you're balancing so that the tower can stand up correctly. If you do not stand the tower up correctly, or if it's not balanced, it will fall over. So that's why you're using geometry at a very young age. This is also the same as balancing an equation in algebra. The equation is not equal and is not solved correctly. Just like a tower needs to be balanced correctly. Are there any questions about the definition of engineering?
No questions, Barry.
Okay, then I just give them a really brief description of the engineering design process. You heard this description on our first day. Basically, I just say that a bunch of engineers got together and they talked about how they solve problems. And a lot of those answers had similarities in them. Now, not all engineers solve problems the same exact way. However, some are very similar. And we call that the engineering design process. And I also tell them that this process can be applied to things besides engineering, really any problem in life or anything that you're trying to accomplish. We can put the engineering design process towards it. Now that they just have a very brief explanation of what the engineering design process is, we pass out a toothbrush. Now, every student gets a toothbrush, and while they are looking at this toothbrush, I ask them to, what are some questions an engineer would consider while designing the toothbrush? The reason I ask this question is because I want students to start thinking about all of the different things that toothbrushes can have. We can have electric toothbrushes, we can have wooden toothbrushes, plastic toothbrushes. The bristles can be made different. You can have a tongue scraper. There's really an endless possibility for toothbrushes. And I'd like to just get them to start thinking. If students are having trouble coming up with ideas, then oftentimes I'll ask them, does the toothbrush in your hand look like the toothbrush at your house? Or do all the toothbrushes on the screen look the exact same? And that usually gets them to start thinking about all the differences toothbrushes can have. Any questions so far?
No questions.
Okay. Manuel, I'm just going to keep going. Could you just stop me if there's any questions or comments?
No.
Perfect, thank you. All right, then what we do is I walk the students through every step of the engineering design process. And this is a very quick process because right after this lesson, they're going to do a hands-on example. Really, all I'm doing is just showing them the different, very briefly, the different steps. So first and foremost, I ask them to define the problem. What problem does a toothbrush solve? And we get a variety of answers for this. One, it solves that your teeth are dirty. You have plaque on your teeth are discolored, your breath is not smelling good. A toothbrush can help with all of these things. But a lot of students will also talk about using a toothbrush to help you clean. So maybe you're helping them clean your shoes or things around the house. There are a big variety of problems a toothbrush can solve. However, one problem a toothbrush cannot solve is a toothbrush can't solve a cavity. So if you have a cavity, you can't use a toothbrush to fix that. You have to go to a dentist. We just talk about problems that a toothbrush can solve and can't solve. Next, we talk about researching the problem. Now for our students, they are very familiar with using the internet. So I'll ask them, if you are typing into Google or if you're typing into the internet, what is a question you can ask about a toothbrush? However, this same thing can be applied to using a book or using a cell phone. Really, it's just where would you go if you wanted to find information about a toothbrush? A lot of things the students bring up is how toothbrushes are made. They might talk about the history of toothbrush. They might talk about different materials or different things a toothbrush can be made of. Or we can also talk about what is the most popular toothbrush, what are toothbrushes people don't like. Those are all different research things we can talk about when doing a toothbrush. After we have this conversation, we go to the next slide. Just developing a solution. I always tell students this is one of my favorite steps because during this step, there are no wrong answers. Students are just coming up with ideas. In the next step, we'll take away some of those ideas if they're not usable. For example, maybe a toothbrush is too expensive, or we have an idea that's just a little silly. But in any case, during the developed solutions, we are just coming up with ideas. But after we came up with just some really small, brief ideas, we talked about creating a prototype. Now, our students do a lot with computer-aided design, which you're going to see tomorrow. So this is a point where we bring that up and say,
I'm from Nigeria, we move forward to Sudan.
Something that you do during the prototype phase. In any case, you are coming up with an example of what the toothbrush could look like in the future if you were going to create it. Right. Then we test and evaluate our product. So if we made a toothbrush, we made a prototype, we need to test that prototype to make sure that it does what we want it to do. And to give them an example of this one, I tell them that I got a toothbrush once And I used that toothbrush one time, and all of the bristles that cleaned my teeth fell out in my mouth. And I was spitting out bristles. So that tells me that the company that made that toothbrush, they didn't test it in a way that met my constraints. And what I mean is maybe the toothbrush got too hot, or maybe the toothbrush sat too long and the adhesive or the glue in the toothbrush deteriorated, it melted away, and it caused the bristles to come out. Whatever the case is, for some reason, the testing and evaluating did not catch that when they were designing that specific toothbrush. Finally, you must communicate your idea. If you create an amazing, perfect toothbrush and you don't tell anyone, then no one's going to know about it and no one's going to buy it. So it won't make you any money if you're in the business aspect. Then you redesign. We really like to emphasize with students that although you are done designing or you like your finished product, you can always make that product better. And that's exactly why the engineering design process is a giant circle. Not all engineering design processes are the exact same. Some have more steps, some have less steps. And oftentimes, you're not going to do the engineering design process in a perfect circle. For example, you might get to step number 6, test and evaluate, and realize that your toothbrush does not do what you want it to do. You have to go all the way back to step 2 and do the research. Then develop, choose, and create again. And I like to also bring up the example of phones and how there are a lot of phones out there and not one phone is perfect. We can always make them just a little bit better with the phone when it comes to a phone. After they've talked about the whole engineering design process, this lesson only takes about 15 to 20 minutes to go through it very quickly, because they do a hands-on experiment that Ms. Bunting is going to show you in just a second, where they're actually able to use the engineering design process. Are there any questions about what we've gone over before Ms. Bunting jumps into her lesson?
Sorry. No questions so far.
Okay, Bunty's going to jump into her example. She's going to roll over a fish tank full of water, so you can see that. Hold on, I'm going to start.
Give us 1 second while we transition. Okay. So as we started on yesterday, when we brought up phenomenon to engage our students in their learning, I start off this lesson with asking students about how do boats work. So I read them this blurb about the USS General R. Ford and how it's the Navy here in the US' largest aircraft carrier. It's approximately 337 meters long. It weighs 1,026 tons. It has a flight deck that is approximately 78 meters wide. and it is capable of carrying more than 75 aircraft and over 4,500 personnel. The kitchen can provide 15,000 meals per day. And so I asked the students, how do these massive ships with their weight stay afloat? And I engaged their thinking by comparing a floaty and a floaty that floats in water. And why does a pebble or a rock sink in water? Most students are able to say because the floaty has air in it and that the rock is heavy. So I asked the students, well, then how do boats stay afloat in heavy water? And so that is our problem that we are talking about for the day, is how is it that boats are able to stay afloat while something like a rock will sink? On the bottom of my screen, I show them a comparison of the ship to a soccer field because I'm trying to engage my students' prior knowledge of maybe watching soccer on TV or playing and allowing them to see that this boat is very similar sized to a soccer field. I then go in and I talk to them about the concept of buoyancy and explain to them that that is the topic that we are going to discuss today. I first ask students how they think atoms or the people in this vehicle might move while they're in there. I engage their prior thinking of what states of matter are tightly packed. And students, for the most part, able to say that solids are tightly packed and that the people in these spaces are not able to move freely. I show them these other two pictures and I tell them again to imagine that these people are atoms and how are they able to move in the spaces that they are in. The students, for the most part, are able to explain that these people are able to move freely and they're not packed together. I again ask which states of matter are not tightly packed, and students are able to explain that liquids and gases do not have their atoms tightly packed. Once we get here, I then bring up that if these molecules and atoms aren't tightly packed and they are able to move freely, the object is not dense. If they are packed tightly and unable to move freely, then the object is dense. And this is how I bring up the vocabulary word density, comparing atoms that are tightly packed to atoms that are not tightly packed. So density refers to how much matter occupies a measured space. The more compact the matter, the denser that material is. I then lead my students in an observation of sink or float, and I'm going to do that with you. Before I continue, does anybody have any questions about how I introduce the concept of buoyancy?
Any questions?
Okay. So I use a fish tank, but you can use any sort of container that holds water. So the first question is I show them, this one isn't a beach ball, but I show them a ball and I ask the students, how is this packed? What do you know about this ball? And they're able to say that this ball has air and it is light, it can bounce. And so I ask them, do we think this beach ball is going to sink or float? All of the students raise their hands and they say this is going to float. Put it in the water.
Well, Kiana, can you hear me?
Yes.
Stop the presentation so we can see the video larger.
Oh, I'm so sorry. You're right. Thank you. Okay. Is that better?
Yes, better. Thank you.
Thank you. Sorry. can start over. So I have the students discuss and look at the beach ball or the bouncy ball that I have, and we discuss whether or not it can sink or float. And most students are able to say that this will float. So I put it in the water and it floats. I then explained to them that on Earth, we have two main forces that are interacting with us at all times. We have one of them, our gravity force, which is keeping us planted onto the ground. And then the other force that we don't acknowledge but exists is our buoyancy force. So if I were to push down on this ball, I am increasing the force of gravity that this ball has, and therefore I'm going against the force of buoyancy. I asked my students, what do you think will happen if I let this ball go as I'm pushing down on it? And they explained that it's going to rise or pop up, to which I then let it go and it rises and it pops up. I didn't do it because I didn't want to get water everywhere. I then show them an 11-pound bowling ball. And I ask them if they think the 11-pound bowling ball will sink or float. And so I'll have them raise their hands, and most students will say that my bowling ball is going to sink. However, I put it in, and the bowling ball will float. It is in a submerged state to where it's not completely underneath and have sank to the bottom of the tank, but it is also not floating like my pink beach ball. The students are then amazed because they did not realize that a bowling ball could float inside of water. I then show them a styrofoam ball, and I ask them to give me the difference between my styrofoam ball and the gold bowling ball that is currently in the water. The students will explain that the bowling ball is going to be heavier than the styrofoam ball. Most students at this time are very confused about why something is floating that is so heavy. And so they assume that my styrofoam ball is also going to sink because water is going to get into it. I then put it in the water, and students will notice that my styrofoam ball is floating. Last, I then take a 13-pound bowling ball and I ask them the difference between this 13-pound bowling ball and the 11-pound bowling ball. Most students are able to say that the difference is the 2 pounds in the bowling ball. And I ask them again, do they think it is going to sink or float, and why? This time, because of my 11-pound bowling ball floating, they are not as confident about answering whether or not something is going to sink or float. So I put it in, and I tell them to watch as the water rises when I put the bowling ball into the tank. So, as you can see, hopefully, the 13-pound bowling ball has sank, and the 11-pound bowling ball is still floating and submerged in the water. So then we get into a conversation about density. So I'm going to pull back up the PowerPoint. But does anybody have any questions about my demonstration of sink or float? No questions?
Anna. No questions for now.
Okay, thank you. Give me 1 second. I'm gonna pull up my PowerPoint again. Okay, so after we've discussed the different objects that float in the water are sank, I then talk about the different types of forces that are applied with force of gravity and our force of buoyancy. So in this image, I have arrows, and I ask the students to see if they can explain which arrow is what. So the down arrow is our force of gravity, and the up arrow is our force of buoyancy. So I ask the students if the buoyancy force and the gravity force are the same, what is going to happen to an object? Students will say it will float. The next one shows if the force of buoyancy is stronger than our force of gravity, what will an object do? This one kind of gives them some questions, but then they're able to think through it and say this will sink. And then I ask them, what about if our force of gravity is stronger than our force of buoyancy? And the answer to this one is it will rise, as they saw with the pink ball. So I explained to them, buoyancy wants objects to rise, like a balloon with helium in it, and gravity wants objects to sink or go down. So when an object floats, that means that their buoyancy force and their gravity force are the same. Does anybody have any questions on how I explain these two forces?
No question for now.
Great. I then give them something that they need to remember. And I say the density of water is 1 gram per cubic centimeter. And I tell them that they need to keep this number in their brain because it is going to come back later. I then show them that we can mathematically solve whether an object will sink or float. And you can extend this further for high schoolers and actually show them the Archimedes, which is the creator of this concept, and how the formula actually is different for high schoolers. But for us doing this with 5th graders, we break it down a little bit simpler so that they are able to understand this concept. So in order to figure out whether or not an object is going to sink or float, we give them the formula to finding the density of an object. So density is equal to the mass of an object divided by its volume. And I also make sure I tell students that fractions are simply just division problems. And so when they look at the problem this way, they are not mixing up whether or not they are dividing and what a fraction looks like. I then have them turn to our density table, where we're going to find the density of all of the objects that we just tested, whether or not they sink or float. So with this example, I have them, and because we have 5th graders and we're not as fast with dividing large numbers, we do give our children calculators to help them divide. However, with older students, you can have them do this math with their hands on pencil paper. So for the first one, we look at the 11-pound bowling ball. I have them take the mass and divide it by the volume. Students will get the answer of 92 hundredths. And we say that this object floated. And so they're able to look at the density and then discuss what it did when we put it in the water. We then take the styrofoam ball and do the exact same thing and find the density of the styrofoam ball, and that is 3 hundredths. And we said and saw that it did indeed float. They do the same thing for the 13-pound bowling ball, finding the density, and they see that the density of the bowling ball is 1 800ths. And the bowling ball sank. I then challenge the students to make an observation of what they noticed about the density of an object and whether or not it will sink or float. I give them 30 seconds of silent think time, as I really want to give them the opportunity to notice the numbers on their density and whether or not this object sank or float. Students are able to look at the number and say that if it's big, it's going to sink, and if it's small, it'll float. I then try and get them to remember that number I showed them earlier, which is the density of water is 1. Once I mention that, students are able to notice that if the density of an object is less than 1, then the object will float. And if the density of an object is greater than 1, which is the density of water, then it is going to sink. I then have the students calculate the density of the clay ball. They have not seen whether or not this is going to sink or float, but I want them to use the knowledge that they just gained from understanding density of an object to see if it is able to sink or float. The answer the students get is 1 600ths. So then I ask the students, without even checking, based off of the density, is my clay ball going to sink or float? And because they have a better understanding of density, the students are able to say that the clay ball is going to sink. I then get a clay ball. I will show you. Yep. I then take my clay ball, I put it in the water, and it does indeed sink. So, right. I then bring us back to that original challenge in the beginning where I asked them about boats. So how is it that boats are able to float? And so I challenge the students to take a clay ball that they each will get, and their job is to turn this clay ball into an object that is going to float. And then once they are able to get it to float, we give them a challenge of adding weight. So it takes about 5 minutes or so for students to start figuring out what it should look like. And I'm going to bring you one right now. So they make the design so that it's spread out of the volume and it has walls around it so that water cannot get in. So I'll put it in the water. And so now what was a sinking object is now an object that floats in water. We give students washers, and their job is to make sure that their boat can stay afloat with as much weight as possible. And this is where we bring in the engineering design process. So students have a problem. They need to be able to have their clay boat float. We research what boats look like so that they understand the shape. And then these students are able to develop possible solutions and constantly test and evaluate their boat. Once students are able to get the clay boat to float, then again, we hand them washers and we count how many washers they can fit in the boat. Their first take, most students can probably get about 3 or 4 washers into their boat before it sinks. We have 2 conversations about why it sinks. The first one is the density of our clay ball. I tell them if it feels too thick, then it is probably dense. And I ask them, what do dense objects do in water? They sink. And so students are able to go back and realize that they need to spread out the volume of their clay ball to get it to float. The second thing that I want students to notice when we're doing this is if their walls aren't tall enough and water gets into their boat, it also then starts to sink. And I ask them why. And most students are able to explain that because water is getting into the boat, it is causing it to be heavier, and so it is going to sink. So then students will then go back, they will fix their clay boat so that they're able to fit more washers on their boat. And we will do this for about 10 to 15 minutes of students going back, creating their design, testing and evaluating it, and then communicating to their partner and others what it looks like, and then going back and creating a brand new prototype for them to test out. And we let students know that this is an okay process to fail while they are creating these boats, because that's what engineers do. They create something, it might not work, they go back and they try again. And that is how we explain the engineering design process with our clay boats. You can do this project with a bunch of different items. So instead of using clay, you can use aluminum foil. You can create it out of popsicle sticks. I know some locations might have a 3D printer, and you can 3D print a boat and still have students test out how many washers or pebbles, rocks, marshmallows, pennies, any sort of thing that has weight. You can have them test how this weight affects whether or not this will sink or float. I then have students come to the conclusion that we do not worry so much about the weight of an object when it comes to density, but the volume of an object. So we have a discussion around boats and how the weight of the boat is less than the volume of the boat. And so that is why boats are able to float. When engineers create boats, they understand that they have to displace or spread out that water so that the boat is able to stay above water. And so students are able to see that when we spread out the volume of our clay ball, it was able to float. And so that is the conversation around buoyancy. This lesson has the engineering design process. We do some information around science. There is math, a part of it. And then the technology piece of using the clay to engage their learning makes hello.
Hi, Perry. Sorry, we lost a good 1 minute. We lost you for about 1 minute.
Okay.
Okay, we are all set here.
Let us know whenever you are ready.
Yeah, we're ready. Hello. You hear me? Can you hear me? I don't know. Hello. 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 Krishna getting us. Yeah, the last one works. Hi, Perry. This one is working. It's going through. Oh, and text up. Okay. Hello.
Hello, we can see you.
Can you hear us?
Can you hear us?
No, we cannot hear you. Can you give us a thumbs up if you can hear us? Okay, great.
Can you hear us now? Hello. Hello.
Daniel, did you want us to keep waiting? Or you want us to go? What would you like us to do? Feel free to check the chat also.
Hello. Can you get us now? So can I hear? Hello. Can you hear us? It's not getting us. Can you check that and let's resolve the issue. Hello. Hello.
Yeah, everything looks fine on our end too.
Can you hear us now?
Yes, we hear you now.
Okay, great. So we can go on.
Where did I lose you with my buoyancy demonstration?
Right at the end, I think we got most of it.
Okay,
Yes.
perfect. I was just ending with that you can do this assignment with anybody from the age of 5 to 17, and then change based off of what you want them to know about buoyancy or the Archimedes principle or understanding density or the concept of displacement, and using this activity as a way to show that sinking and floating is more than just objects being heavy or not heavy.
All right.
Does anyone have any questions or thoughts or discussions around engineering design process or activities they do in their class to engage their students around the engineering design process?
Any questions? Okay, we have some questions.
Great.
Hello. When you present the steps of the engineering design process, I saw them equally just the same as the design thinking process. So I wish to know the major difference between the engineering design process and the design thinking process.
I agree, because those are two different processes. And most students in their elementary school career will learn the scientific method or process, but we do not teach the engineering design process to students in elementary school currently.
Okay, another question.
Okay, I understand that your lesson is about density, and one thing that I've picked up from there is the fact that you try to let the students keep in mind that the density for water is 1 gram per centimeter cube. My question is this, with that lesson, do we assume that your students have prior knowledge of base physical quantities? I mean, like volume and mass, and they do know how to measure and the various equipment that are used to measure these quantities before coming to density as a lesson? That is my first question. And then the second question is, at what time do you teach the students the notion of SI units? Yeah, because we know that the SI unit for mass is the kilogram, but at this stage, they are still using the grams and stuff. At what stage do you teach the students all of that? Thank you.
Okay, so to touch on your first question, most students in 5th grade understand the definition of mass. I do tend to give a quick, brief explanation that mass and weight are 2 different things, and mass is related to our gravity. Oh,
Can
do
you
we
hear you?
agree? Yeah. No?
Hello.
Yes, well, we kind of explain about the mass, and then
Hello,
students,
can you hear you?
yes. Oh, hello? Uh-oh. What happened to our sound?
We couldn't hear you answering the question at all.
Oh, no, okay.
Can you hear us now?
Yes, we can hear you now.
My goodness. I know. I will tell students about the difference between mass and volume and how mass relates to our gravitational weight on Earth. Students do learn about volume in the 5th grade, but the purpose of this specific lesson is to understand density. And the lesson doesn't go as deep as it could with mass and volume. But we do touch on it a little bit for them to understand that the volume does need to be greater than the mass for an object to float. As to your second question, we start teaching units of measurement to students at about the age of 8. With this lesson, we do keep it pretty simple with it being grams. I will also say that in America, we use the imperial system. So students tend to learn more when it comes to like inches and feet, miles. And so when they come to us and we use the metric system, we do need to keep it pretty basic, as it is not as strongly taught here in America to use the metric system. So students have to learn imperial first, and then we do teach them the metric system, but it is not something that they use as they get older, just because that's how our system is here in America, if that makes sense.
I would like also to add that we do have to have a conversation about what is a gram per centimeter cubed. It is a difficult concept to picture. So when we explain exactly what that means, students get a better idea of what we're talking about. Also, at this age, we are focusing a lot on what specific units we use for a given task. So if we're using length, we're going to be using centimeters, inches, meters. If we're using mass, we're using grams, ounces. So really our focus a lot of times is on which unit you're using for a given situation.
Thank you, Perry. Any other question? Okay, we have no other questions for now, so I think we can proceed.
Okay.
So Manuel, at this part of the meeting, we have that we're going to be doing a Cameroon demonstration. We weren't sure exactly what we were going to have that look like. Did you have any ideas there?
Well, we have a recording of our own EDPs that we've tried to implement here during our summer camp, so we could play that for you to see how we've implemented EDP here in some
Perfect.
situations here.
That's great. Thank you.
Open the web browser and go to YouTube. No, egg drop. Egg drop. No, midnight. Egg drop. Egg space drop. Share. Okay. Perry,
Yes.
we're not able to share our screen on this end.
Oh, I can do that.
Oh yeah, let's give you permission.
Just 1 second. Okay, now go ahead and try.
Okay, so can you see our screen?
We can see your screen.
It's your screen.
So the very first EDP activity that we usually start with is the very popular egg drop challenge. So it's quite very basic and straightforward, and then students can do a lot of redesigning. The aspect of redesigning is seen a lot because the aim of the EDP is of the egg drop challenge is to drop an egg from a certain height and not have it break. And then they use very basic and rudimentary materials like balloons, cardboard papers, styrofoams. What do you have in your mattresses? Yeah, so we use really basic things. And then I think once we did it, last time we did it, we were at on this floor or 2 floors high, and then they have to drop an egg. We'll team them up, about 5 teams of 3 or 4 people each. They have to design a structure around their egg and then drop it from that height and make sure it does not break. So if the egg breaks, you fail, and then you have to redesign until you come up with a design that is, and the conditions that we set is the design has to be minimalistic in the sense that it should fit in a certain box. So we use a 30 centimeter by 30 centimeter box. Your design should fit in that 30 centimeter by 30 centimeter box. So we don't have people putting their entire egg in a whole teddy bear or whatnot. So we constrain them. Your design should be able to fit in that 30 centimeter by 30 centimeter box. And then it should use only what we've made available for you. So this is what we made available. Get creative, and then make sure your egg does not break. So we'll play a very short recap, about 1 minute, 30 seconds video of the last egg drop challenge we did. So I'll play that.
I ain't got a clue how to spend my time. This ain't nothing new, you've been on my mind. I ain't got a clue how to spend my time. This ain't nothing new, you've been on my mind. Yeah, you know, I know when you hit my phone that you gone and you ain't calling back, no. But lately I'm lost and I don't think you know that I want you this time. I don't need you. I'm on my place in the moment, I just want you to be. All of these other guys, people, they ain't got nothing on me, yeah. Man, at least swimming in circles, I'm taking you out to the beach. Go and look in the mirror, do you see the same as me? Got me in the first day, I'm meant to lose my mind. What else to do? Think about you all the time.
Voilà, this is easy. The egg was like,
So I can ease your mind. I can ease your mind. Oh, let me ease your mind. Ain't got a clue how to spend my time. This ain't nothing new. Been on my mind.
Everybody won now.
Okay. So that was our own implementation of engineering design process in a very simple challenge that can really get kids started, get them creative. And from there, we moved on to another experiment, the Mars Lander mission. I don't know if you have the video here. So that one was a little bit more complex, where they had to take a lot of factors in place. It's not uploaded yet. So that is a demo from here. So any thoughts?
Okay, that was a great video. Thank you for sharing. So I noticed that you have some different constraints. One of them was the size of the object and the materials they're going to use. Do you also, I saw a timer on the board. Is that a limit on how long they get to build?
Exactly, yes.
Time as well. What age range was in the video?
So we had students from about 8 years to 14 years old.
8 to 14. Wow. Either before or after that, what does the conversation about the engineering design process look like with those students?
I didn't get you.
Either before or after the egg drop,
Mhm.
what does the conversation about the engineering design process look like?
So initially, when we introduce EDP, the students are quite confused as to how they have to go about the entire process. They can see the graph, they can see the entire cycle, but then they get very confused about at what level are we redesigning, at what level are we testing, at what level do we know we have a final design. So once they start, you saw the constraints that we gave them, and then they did some pre-testing, just dropping from table height, and then as they move through, making sure that the egg doesn't break at table height, and then at a floor 2 level height, they are able to understand that okay, they can match each aspect of the entire engineering design cycle to what they are currently doing. That is first, and they did prototyping too. So they rapidly prototype what they wanted their structure to look like. They did prototype on papers where they drew designs. And one of the other concerns was two teams should not have the same designs. So each team had to come up with their own very unique design. So they had to brainstorm on the designs that could work, then test the designs that worked, and then the ones that didn't work, then reiterate that. So by the time they were done and were able to safely land their egg on ground level without it breaking, they were able to understand the different aspects they need to go through if they're trying to develop a viable solution. So EDP became a lot more understandable once they were through with this very little experiment.
I would love to hear if anybody else in the room, how do they teach the engineering design process to their students?
Has anyone else done EDP with your students and the experience with it? No one else? I'm asking if anyone else has had the chance to implement the engineering design process with their students. So can you share about what the experiment was and how you went about it?
Okay, good afternoon. Yes, it was not really an experiment, but a construction process, because where I used to teach before, there was this club called the engineering club. So every Friday we have to choose a project, like something to build a prototype of something that we see online, or maybe a house, a car, or Bob, or any physics project that we see, or any engineering design, like we can take a graphics designing. So it was all about just engaging the students into that engineering design process approach, finding problems and bringing solutions to it. So every Friday, we have to identify a project to build. So on several occasions, I will start from a house. I think I still have the image of the house. We built a house with cartoons. That is a whole house with a gate and doors, windows, with using these cardboards and the pins and the melting instrument used by these electricians. Yes, with the gum. Yeah, something, the soda. So yes. So, okay, thank you. So we build with it, and then we construct a whole house. So they get to understand that constructing a house needs this equipment. It needs you to first of all do the design. So sometimes we draw the designs first using our computers. Then now we go into the construction. Then sometimes we have to go to the carpentry workshop to see what the people do there before we come now to implement our project back in school. And then sometimes we go to an open space, maybe to a fish pond, to study the area and how the person controlling it, or the owner, gets to put the pond and how he manages the pond and how whatever happens there. Now we come back in school, we come to implement what we have seen at the pond.
That is amazing. It's very cool what you're doing with your students. Very real world.
I'm impressed that they're able to use a soldering device. That's not easy to do.
Anyone? Okay.
Basically, my projects are mostly with 16-year-old students who are in high school. We design almost everything that is in the lessons. I will take an example of a project for house wiring, creating for them wiring a house using the ringway switch system, and then using parallel connections and series connections. Now, I always start by asking them to get electric cables. We discuss first of all the project, what the project is all about, and then we have a day that they'll go to the carpentry shops. They buy, first of all, they can get plywood or they get cardboard papers, and then with switches. You have modest switches that they sell at the electrical shops, and then what they use are 9 volts batteries, DC batteries. Now, when they come, I always insist that the project, they should try it out at home, and then they use light bulbs of maybe 3 volts, 1.5 volts. Now, whenever they come, they do a demonstration, each of the groups. They actually have to do a demonstration and then explain why their project could not work and how they improve on the project. And then with this one is on electricity, and then every other project, we ensure that we discuss it. We discuss the science, I always say the science process or the engineering design process, such that they master it and then they put it into practice. And then I've had students that have actually built amplifiers at the level of the school. Now building the amplifiers, they apply the engineering design process. And then when they come, they present in school. So most of the projects are carried out at home, within the community, and then they come and then do their presentations. Thank you.
All right, just to clarify, you're building amplifiers?
Yes. Sound amplifiers, right? Yes.
That's amazing. Just a quick question about that. Are students working on their own or are they working with others?
The students actually work in groups. They work in groups. We don't allow individual students to engage into the projects because they have to do it, but precisely they work between 6 to 10 persons per group. Since the materials, they get those materials themselves, don't provide the materials, so they have to buy, and it makes it easier for the students who, when there are more students, like between 6 and 10, they actually spread the cost.
And I like how you mentioned that you have students explain why their idea didn't work. I think that's a really nice add to the end. I think that's neat.
Thank you. When the students actually indicate why or how they did not work or the project could not work, we identify that it is actually because of poor electrical conductivity. If you don't ensure good contact between the wires, it will not work effectively.
So are the students soldering for this project also? Or how are they making these connections?
Pardon?
Or how are they making the connections between the electrical components? Are they soldering?
When they have a continuous loop, of wire, and then the point that they do the connections there may not be well connected.
Got it.
Okay, I just want to talk about, it's an experience of two kids in Bamenda. One is 8 years, another one is 5. They used to play a lot, and the 8-year-old realized that he can use plastics and turn it to something useful. So whenever there's a container like a 1.5-liter transparent, he's going to take a scissors, he'll take a sharp knife which is warm, he'll shape it out to plain straight equipment, and he's going to produce a toy frog with his junior brother, so that when he has the way that he makes it, when you touch it, the frog is going to jump. It's going to jump, and they actually put that in water, and that helps to control them, and he's more creative because he trained his 5-year-old junior brother to start imitating the process. I don't actually know how they came about that, but that was an interesting way to keep them home. With that, it was really interesting that you don't see plastics around their house or papers. They'll turn it to a toy frog, and they're going to press it and make crack. And it's really something very interesting. So that was an observation.
Okay, please, I just wanted to share a project that I carried out with Form 1 students of my school. It's actually a game. I don't know if we can put it so they see it. It's a square. Okay, I will just send it on the WhatsApp group. It's a square, it's a game made up of a square frame, now with cups attached inside the square frame. So there are cups inside the square frame. When you play the game by using a ball, so you put the ball in one of the frame, in one of the cups on one side of the frame, and then you try to turn it. When you turn the frame, the ball should jump, it should go directly into another cup on the other side of the frame, and if you turn again, it should go again in the other cup on the other side of the frame. So it helps the students to think critically. How are we going to put the distances so that the ball will just leave the one cup to the other, and how will keep on, because you're kind of turning, as you're turning the object, the ball has to be on the frame. So it helps also, it helps for relaxation, and it helps for critical thinking. Yes. So this is a project we built with the Form 1 students of my school.
Wow, that is such a fun game. I want to make that.
Yeah, we want to make that here.
Any other First wants to chime in?
Um, Concerning things related to that, I want to say, from my experience, during the summer break, what students actually do, we have an organization called the Tech Innovation Center. That one, it deals with actually helping students to solve real life problems. So showing how they can produce robots. They have to go through. That's why I was asking the difference between the engineering design process and the design thinking process, because actually they go through the design thinking process, come up with how to produce robots. Most of the time they have to program these robots. So they go through a period of like 2 to 3 months. They actually program the robots, and at the end of the day, they're able to come out with robots, even though the sizes are small, but which are functional and can actually carry out the tasks of a real robot. Some demo videos are online from the past editions of the bootcamp.
Sorry, just to clarify, what exactly are they creating?
Pardon?
What exactly are they creating? You said they're creating.
Yeah, they're creating robots like aeroplanes. Some are just robots that can. Yeah, one of it is like an aeroplane.
Oh, an airplane.
Yes.
Oh, okay, gotcha. That's really neat.
Yeah, I have one I want to share. Once more, good afternoon, everybody. Yes, my experience came when I was teaching in Form 2 about types of forces. And when one student was so smart and kept on asking me, so you've taught forces, but I've heard of planes and especially the rocket. The student asked me, how does a rocket fly? That was a question the student asked me in Form 2. Then now I explained about the thrust force, and I had to really think and see what I could design for this student to understand and have a perfect mastery. So now I took these balloons. I took 2 big balloons, and then I make sure that I inserted one inside the other so that at least when I blow it, it will not get blown. Then we use this typing sheet, this are normal sheet, and then we curve the shape of a rocket. And then when we blow it now, we allow it and then open it. The air was coming behind and then it was going ahead. And I explained that this is the technology behind the rocket. The child was extremely happy, and that child promised to do more. In our school last time, the vice principal called me that one child designed something, but I'm sorry, I've not had time to really check. Thank you.
It's a really creative way to teach thrust.
Yeah. Okay, one other contribution.
Hello all. Yeah, the experience I want to share is linked about the electronic courses. Teacher in class 2. When I did the course, I first do the theoretical lesson to teach how there is voltage and what is voltage, what is intensity of current. Then I make a scheme, a schema. So the student knows really what is the montage. So after that, I tell them to do the same thing at the home with her own equipments, with their own cables and lamp and batteries. Then to show it's amazing experience because some of them make a variation of the number of battery and take the conclusion alone. So they see how when we put together a number of batteries, we have the lamp who, I don't know, briller, c'est quoi? Bright? Briller. Yeah, the lamp will brighter variously, and that is amazing experience because the students make the conclusion alone, and that's feeling, that's amazing experience. It's what I want to share with you. Yeah, thank you.
Thank you.
Do a lot of work with electricity. I'm really impressed.
Yeah, we're doing a lot of things with electricity. His experiment is basically changing the voltage and current and seeing how the brightness of a bulb changes. Yeah, then students can understand that. So another engineering design process activity that we've done here, very similar to the egg drop challenge, but then really applying a lot of what they learned on the egg drop challenge to other things. This experiment, the Space Lander mission, was actually pulled up from the NASA website. So it gives our students the ability to dream, to know that these things are doing here, they could be working for NASA tomorrow. The Space Lander experiment, I was linked in the chat, is basically for students to design a rover that will land 2 astronauts. In this case, we use marshmallows, and we actually use marshmallows. So the 2 astronauts will be placed in the rover, and then they should be able to land on the moon without one falling out of it. So we replace astronauts with marshmallows here, and have the students design a structure, a rover, basically that will carry these 2 astronauts. They should be able to land safely on the moon without tilting and without the astronauts falling out of the rover they designed. So I'll play a short video that is a recap of what they did, the process and the design they came up with. Okay. So that's basically the recap, and then these are the ones that won. That is what their structure looked like. In this experiment, they had to use straws, paper, plastic cups, and cardboard papers, some tape, and glue.
How did you determine this group as the winner opposed to the other groups?
Well, this was a group that won. None of the astronauts fell out of the cups. And we had a little bit of dust around where they were landing. I'm not sure you could see that on the video. And then the structure that raised less amount of dust, and that was more stable. That kept the structure when landing. Because some will land and they will break and then they'll fall apart. The astronauts might not fall out of the astronaut might not fall out of the structure, but the structure doesn't retain the entirety. So this particular structure withstood the landing. It raised the least amount of dust, so it was very stable, and the astronauts did not fall out at all. So they got to eat the marshmallows because they were not soiled.
I see. I really like what they did with the paper. I think that was a really good idea for the landing. That's amazing. It's like a
Yeah, you
spring.
They changed the papers into springs, so that could really absorb the shock, and that was all left to them to be creative about it. We give them the materials, and then they had to come up with a creative structure that will absorb shock on impact and maintain the entire structure together.
See.
Okay, is there another contribution? I think that is it for the Cameroon demo. This is what we have to show on how we've been implementing things on our end here.
Great.
No, yeah, that was awesome. Thank you so much for sharing.
Manuel, I do have one question. Wondering if you could answer it. We've noticed a few times that you've mentioned the science process and the engineering design process. Are those, could you tell us a little bit more, what exactly is the science process?
Can you elaborate on the science process? Some people were mentioning the science process, so they want to get more light on that. The scientific process. Some people were mentioning the scientific process. So I personally am not very.
The science process is, like I always say, is basically the same like the engineering design process, because with the science process, you have to define the problem. That's the first thing. You must define the problem, and then you set out a strategy, first of all, on how you solve the problem. And that strategy, you follow a research. You not do a research